this videotape, we're going to learn how to differentiate the trig functions. Okay, and in the course of this videotape, I'll be introducing you to 6 new differentiation formulas, one for each of the 6 trig functions. Before we get to that, however, let's review the main rules for differentiating algebraic functions. Okay, we have 4 basic formulas for differentiating algebraic functions. The first is for differentiating a constant times x to a power. This is very useful for differentiating polynomials or any function which is a sum of terms, each one of which is a constant times x to a power. If you have to differentiate a constant times x to a power, as we have in the first line here, the derivative of a constant times x to a power is the constant times the power x to the 1 less power. In the second line, we have the product rule. If you want to differentiate a product of 2 functions, the formula calls for the derivative of a product is the first function times the derivative of the second plus the second function times the derivative of the first. In the third line, we have the quotient rule. When you want to differentiate a quotient of 2 functions, the derivative is the function in the denominator, the bottom function, times the derivative of the numerator, the derivative of the top function, minus the top function times the derivative of the bottom, all over the bottom squared. That is, the derivative of a quotient is the bottom times the derivative of the top, minus the top times the derivative of the bottom, all over the bottom squared. And finally, we have our power rule. This is for differentiating a function to a power. The derivative of function to a power is the power times the function to the 1 less power times the derivative of the inside. That is, power function to the 1 less power times the derivative of the inside. Okay, now we assume that you've already mastered the rules for differentiating algebraic functions. And as I said, we're going to be introducing 6 new formulas today for differentiating trig functions. It will not be enough, however, simply to memorize these 10 formulas. You have to know which formula to use in which cases, and it's not always so easy. Let's start with the following example. If y is equal to the sine of 3x, let's assume we want to find dy dx, the derivative of y with respect to x. Now, this, of course, does not come under any of the 4 formulas that we've already learned. Let's look now at the derivatives of the first 3 trig functions. The derivative of sine of a function is the cosine of the same function times the derivative of the function. The derivative of cosine of a function is minus the sine of the same function times the derivative of the function, and the derivative of tangent of a function is secant squared of the same function times the derivative of the function. Now, in this first example, we're going to be looking at the first formula, the sine of a function. Remembering the derivative of a sine of a function is the cosine of the function times the derivative of the function. We see that this first example comes under the category sine of f of x. It is sine of a function. The derivative of sine of a function is cosine of the same function times the derivative of the function. Cosine of the same function times the derivative of the function. A common mistake that students make is that they write down the cosine of 3, the cosine of the derivative. That's not correct. The derivative of sine of a function is cosine of the same function, then multiply by the derivative of the function. Also, if you put the 3 in front, you can dispense with the parentheses. 3 cosine 3x is a neater way to write the answer, although this, of course, is correct. The derivative of sine of a function is cosine of the same function times the derivative of the function. Now, to give you an idea of how things can get a little confusing, let's look at the next example. Y equals sine 5th 3x. Now, when you see a power right after the name of the trig function, this means that this is really sine of 3x all raised to the 5th power. Okay, so this is an abbreviation which eliminates the need for the parentheses. Sine 5th 3x means sine of 3x all raised to the 5th power. Now, suppose we want to find dy dx in this case. All right? Now, I see the sine 3x just like you see it. And since I just taught you this new formula for differentiating sine of a function, there's a strong temptation to use it. However, this is really not primarily a sine of a function problem. Primarily, this is a function to a power. So it's really one of the rules that we learned, the power rule, that we learned in an earlier videotape. The derivative of function to a power is what we have to handle here. You'll get your chance to use the derivative of sine. Don't worry about it. But right now, you have to ask yourself, what is this primarily? Polynomial, product, quotient, power, or sine? This is primarily a power. It's a function to a power. The derivative of a function to a power, we know, is the power times the function sine of 3x to the 1 less power times the derivative of the inside. The derivative of a function to a power is the power times the function to the 1 less power times the derivative of the inside. Now, you have to ask yourself, well, what is this inside function? The inside function is sine of something. And we know the derivative of sine of something is cosine of the same something times the derivative of the something. Of course, the derivative of sine of 3x we had already calculated to be 3 cosine 3x. So this requires us to use two formulas. First of all, to say this is a function to a power, differentiating by the power rule. We get power function to the 1 less power times the derivative of the inside. But what is the inside? Sine of something. So the derivative of sine of something is cosine of the same something times the derivative of the something. So cosine of 3x times 3. And we can write this answer as, let's see, 5 times 3, that's 15. Sine of 3x to the 4th power, we can write sine 4th 3x and eliminate the need for the parentheses, cosine of 3x. So 15 sine 4th 3x cosine 3x. For our third example, let's look at y equals the cosine of 5x over 3x squared plus 4. Now, when we look at this, we see a quotient and we see a cosine. You have to ask yourself, what is this primarily? Is it primarily a quotient? We need to use a quotient rule. Or is this primarily cosine of something? And of course, the answer is that this is cosine of a function. And we need to differentiate by the cosine rule. Let's look at the formula for the derivative of cosine. The second formula here, the derivative of cosine of a function is minus sine of the same function times the derivative of the function. Okay, let's go back to our example. dy dx for this problem, we have here cosine of a function. The derivative of cosine of a function is going to be minus sine of the same function times the derivative of the function. It's cosine of a function. The derivative of cosine of a function is minus sine of the same function times the derivative of the function. Okay, now you have to ask yourself, what is this that we have to differentiate? This, of course, is a quotient. So to differentiate this function, over here we have to use the quotient rule. The derivative of a quotient is, of course, the bottom times the derivative of the top. The derivative of 5x with respect to x is 5, minus the top, 3x squared plus 4, times the derivative of the bottom, the bottom times the derivative of the top minus the top, 5x, times the derivative of the bottom, which is 6x, all over the bottom squared. Okay, so we have cosine of a function. The derivative of cosine of a function is minus sine of the same function times the derivative of the function. Minus sine of the same function times the derivative of the function, but this, of course, is a quotient. We need to differentiate it by the quotient rule. The derivative of a quotient is the bottom times the derivative of the top, which is 5, minus the top times the derivative of the bottom, which is 6x, all over the bottom squared. And of course, this can be simplified, but we're not going to work on that right now. The important thing we're trying to do today is to learn these 6 new differentiation formulas and to be able to combine them with the 4 that we already know and know when to use which formula. And very often in a problem, you need to use more than one. So for example, over here we had the cosine of something. The derivative of the cosine of something was minus sine of that something times the derivative of the something, but this something was a quotient. And we differentiated by the quotient rule. Bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. For our next example, let's look at the following. Y equals the tangent of the square root of 3x plus 4. This is an example of tangent of something. We will differentiate this by the tangent rule. Let's look at the formula sheet and look at the rule for differentiating tangent of a function. The bottom formula, the derivative of tangent of a function is secant squared of the same function times the derivative of the function. Okay, back to the board. If y is the tangent of the square root of 3x plus 4, this is tangent of something. To differentiate this, we will write secant squared of the same function times the derivative of the function. The derivative of tangent of a function is secant squared of the same function times the derivative of the function. Now, when we have a very simple example, sometimes we can do this extra differentiation in our head. However, in this example, this differentiation is itself something that needs work. Okay? So what you can do is just write down. It's going to be secant squared of the function times the derivative of the function. And on the next line, we'll fill in the derivative of that function. Okay? It's a good idea to do this so that you don't lose the train of thought. Secant squared of the same function times the derivative of the function, and then we'll fill that in later. Okay? Now, think about that function that we have to differentiate, the square root of 3x plus 4. Try to figure out which formula that's going to come under. In order to do that, we need to remember that the square root of 3x plus 4 is really the same as 3x plus 4 to the 1/2 power. The square root of 3x plus 4 is 3x plus 4 to the 1/2 power. So if we want to differentiate the square root of 3x plus 4, what we're really trying to differentiate is 3x plus 4 to the 1/2 power. Let's write it that way. We want to differentiate 3x plus 4 to the 1/2 power. In this form, we are better able to see that this is an example of the power rule. It's a function to a power. Okay? Remember, the square root of 3x plus 4 is the same as 3x plus 4 to the 1/2 power. So when we want to differentiate the square root of 3x plus 4, we're differentiating a function to a power. Okay? So we have, from before, secant squared, square root of 3x plus 4, and now we have to multiply by the derivative of 3x plus 4 to the 1/2 power. But the derivative of 3x plus 4 to the 1/2 power by the power rule is the power times the function to the 1 less power. 1/2 minus 1 is minus 1/2 times the derivative. So let's see what we have so far. The derivative of tangent of something is secant squared of the same something times the derivative of the something. The derivative of the square root of 3x plus 4, however, was the same as the derivative of 3x plus 4 to the 1/2 power. In other words, we needed to use the power rule. The derivative of a function to a power was the power times the function to the 1 less power. 1/2 minus 1 gave us minus 1/2 times the derivative of the inside. The derivative of 3x plus 4 is 3. Okay, let's clean this up and see what we get. Well, we have a 3 upstairs. We have secant squared of the square root of 3x plus 4 upstairs. we have a 2 downstairs. Now, see, the 3 is in the numerator. If we were to continue the division sign here, the 3 is upstairs, the secant squared, the square root of 3x plus 4 is upstairs, the 2 is clearly downstairs. Now, let's look at 3x plus 4 to the minus 1/2 power. 3x plus 4 to the minus 1/2 power goes downstairs as 3x plus 4 to the plus 1/2 power. Okay, when you have something to the minus 1/2 power upstairs, it can go downstairs to the plus 1/2 power. All right? So we can write this answer as 3 secant squared, the square root of 3x plus 4 over 2. Now 3x plus 4 to the 1/2 power, remember, is the same as the square root of 3x plus 4. So our final answer to this problem is 3 secant squared, the square root of 3x plus 4 over 2 times the square root of 3x plus 4. Let's go back and look at it again. We started with tangent of something. The derivative of tangent of something was secant squared of the same something times the derivative of the something. Okay? But the something was the square root of 3x plus 4, and we saw that that was the same as 3x plus 4 to the 1/2 power. So we needed to differentiate 3x plus 4 to the 1/2 power, and we did that by the power rule, giving us power, function, 1 less power, derivative of the inside, and then we just cleaned it up a little. The 3 was upstairs, the secant squared, the square root of 3x plus 4 was upstairs, the 2 is downstairs, and we saw that 3x plus 4 to the minus 1/2 went downstairs to the 1/2 power, and that, of course, became the square root of 3x plus 4. Now remember, you cannot cancel these square roots of 3x plus 4, because that would leave the secant squared of, and you can never have a trig function without an argument right after, without an angle right after it. It can't be secant squared, it has to be secant squared of something. So you cannot cancel these square roots of 3x plus 4. For our next example, let's look at something which is pretty similar to what we just did. Instead of tangent of the square root of 3x plus 4, I now want to do the square root of the tangent of 3x plus 4. Okay? Here we had the tangent of the square root of 3x plus 4, and this was an example of tangent of something. And we differentiated it, and we got secant squared of the same something times the derivative of the something. Okay, now this looks similar, but it's really quite different. We have here the square root of the tangent of 3x plus 4. This is really tangent of 3x plus 4, all raised to the 1/2 power. The square root of something, we've seen, means that's something to the 1/2 power. So this is primarily a power. It's a function to a power. So for the moment, ignore the fact that we have a tangent. Just think of this as something to a power. The derivative of something to a power is the power times the function to the 1 less power, 1/2 minus 1 is minus 1/2, times the derivative of the inside. The derivative of a function to a power, and that's what this is primarily. This is a power. Derivative of a function to a power is power times the function to the 1 less power times the derivative of the inside, but the inside is tangent of something. And how do you differentiate tangent of something? It's secant squared of the same something times the derivative of the something. So we have power, function, 1 less power, times the derivative of the inside, but the derivative of the inside, the derivative of tangent of something, is secant squared of the same something times the derivative of the something. So secant squared of 3x plus 4 times the derivative of 3x plus 4, which is 3. Okay, let's see if we can simplify this answer. Well, we have, once again, a fraction for an answer. The 3 is upstairs. Secant squared of 3x plus 4 is upstairs. This 2 is downstairs. the tangent of 3x plus 4 to the minus 1/2 power comes downstairs as tangent of 3x plus 4 to the 1/2 power, but that goes down as the square root of the tangent of 3x plus 4. The 3 secant squared of 3x plus 4 was upstairs, the 2 was downstairs, and this tangent of 3x plus 4 to the minus 1/2 power goes downstairs to the 1/2 power, which is the same as the square root. Okay, let's look at these two examples one more time just to see, because as I said, it's not enough to know the power rule and to know the rule for differentiating tangent of something. You've got to know which formula to use and when. Okay, this first example was tangent of something. Okay, and that starts by secant squared of the same something times the derivative of the something. And here's where you get your chance to use the power rule. So here you start with tangent and finish off with power. However, in example 5, the square root of tangent of 3x plus 4 was tangent of 3x plus 4 to the 1/2 power. This was the power rule. This was primarily a power. Power, function, 1 less power, times the derivative of the inside. So you started with the power rule, and then you get your chance to use your tangent rule. Okay, but the order in which you use them is very important. In our next example, we introduce another of the trig functions. We have y equals x cubed times the secant of 5x plus 4. But let's analyze this first before we look at any formulas. This is what? Well, I see the secant of something, but primarily this is a product. It's x cubed times the secant of something. Okay, so it's a product. So we will differentiate by our old friend, the product rule. It will be the first x cubed times the derivative of the secant of 5x plus 4 plus the second function, the secant of 5x plus 4 times the derivative of x cubed. Okay, so what we're dealing with primarily, even if you don't know the derivative of secant yet, what we're dealing with here is a product. It's a product of two functions. The derivative is the first function times the derivative of the second plus the second function times the derivative of the first. Now this will give us x cubed times the derivative of secant of 5x plus 4 plus secant of 5x plus 4 times the derivative of x cubed with respect to x. Of course, that's 3x squared. So the only thing we need to know here is what is the derivative of secant of something. Let's look at our formula sheet, and we see the derivative, the middle formula, the derivative of secant of something is secant of the same something times tangent of the same something times the derivative of the something. The middle formula, the derivative of secant of something, is secant of the something times tangent of the something times the derivative of the something. Let's go back now to the blackboard. We have x cubed times the derivative of secant of 5x plus 4, but the derivative of secant of 5x plus 4 with respect to x will be secant of 5x plus 4 times tangent of 5x plus 4 times the derivative of 5x plus 4 with respect to x, which is 5. Okay, so we were dealing primarily with a product. So what we had was the first function times the derivative of the second plus the second function times the derivative of the first. Now the derivative of the first was easy enough. That was just 3x squared. When it came to the derivative of the second, that was secant of something. That's our new formula. The derivative of secant of something is secant of something times tangent of something times the derivative of the something. And of course, this could be simplified. You could write this as 5x cubed secant of 5x plus 4 tangent of 5x plus 4 plus, and you can write the 3x squared in front, 3x squared secant of 5x plus 4. Let's do that. 5x cubed secant of 5x plus 4 times tangent of 5x plus 4 plus 3x squared times the secant of 5x plus 4. For our next example, let's try the following. Y equals the cosecant of 3x plus the cotangent of 5x. And we want dy dx. Well, this is a sum of two functions, and we have already learned that the derivative of the sum of two functions is the sum of the derivatives of the individual functions. So we're going to be adding the derivative of this to the derivative of that for the derivative of y with respect to x. Okay, what we need is the formula for the derivative of cosecant of something and of cotangent of something. Let's look at our formula sheet. And on the bottom we have cosecant of something. The derivative of cosecant of something is minus cosecant of that something, cotangent of the something, times the derivative of the something. And on the top line we have the formula for the derivative of cotangent of something. It's minus cosecant squared of the function times the derivative of the function. Okay, well, we'll need the first and the third formula from that sheet to do this problem number 7. Let's go back to the blackboard. The derivative of cosecant of 3x is going to be minus cosecant of 3x times cotangent of 3x times the derivative of 3x, which is 3, plus the derivative of cotangent of 5x, which is minus cosecant squared of 5x times the derivative of 5x, which is 5. So the derivative of cosecant of something is minus cosecant of that something, cotangent of the something, times the derivative of the something. The derivative of cotangent of something is minus cosecant squared of that something times the derivative of the something. And we can write our answer as minus 3 cosecant 3x cotangent 3x minus 5 cosecant squared 5x. For our next example, let's try the following. Y equals cosine of x times the tangent of 2x. Cosine of x times the tangent of 2x. We have to ask ourselves, what is this primarily? Now, I see the cosine and I see the tangent. But primarily, this is a product. It's really cosine of x times the tangent of 2x. You have to be able to see this as a product to be able to do this. Then, when we want to differentiate it, it's going to be the first function times the derivative of the second plus the second function times the derivative of the first. And you can even write first function times the derivative of the second plus the second function times the derivative of the first to keep track for yourself. Okay? This is better than just leaving it and doing only half. What happens is sometimes people get all excited. They know it's the product rule. They go first times the derivative of the second, but they get so bogged down in doing the derivative of the second that they forget to go back to second times the derivative of the first. So first you should go through the whole product rule and map it out, and then you'll fill in what you need. Okay, let's recall the formula sheet that had sine, cosine, and tangent on them, and we will have what we need. The derivative of cosine of something is minus sine of that something times the derivative of the something, and the derivative of tangent of something is secant squared of that something times the derivative of the something. Okay, let's go back to the blackboard. The first times the derivative of the second. The derivative of tangent 2x is secant squared 2x times the derivative with respect to x of 2x, which is 2. So it's first times the derivative of the second, but the second was tangent 2x, and the derivative is secant squared of the same function, 2x, times the derivative of 2x. And the derivative of cosine x is minus the sine of x. Derivative of x, of course, is just 1. So just minus sine of x is all we need. First times the derivative of the second plus the second times the derivative of the first. For our next example, let's look at something which is quite similar, at least in appearance. Y equals the cosine of the tangent of 2x. Now, some people mistakenly think that this is a product. But it can't be a product because cosine can't stand alone. It has to be cosine of something, always cosine of some function. So over here was cosine x times tangent 2x. Remember, originally, the problem did not have the parentheses. I put them in just to help you. This is the way you're more than likely to see the problem. Cos x tan 2x. And here, cosine of tan 2x. The difference is that this is a product, because cosine x can stand alone, tan 2x can stand alone, so this must mean multiplication. However, cosine can't stand alone. What we're dealing with here is cosine of something, okay? Cosine of squiggle. This is not a product. This is a cosine of squiggle problem. Well, the derivative of cosine of squiggle will be minus sine of squiggle times the derivative of squiggle. The derivative of cosine of squiggle here will be minus sine of squiggle times the derivative of squiggle. Now let's look at squiggle here. Tangent of 2x. You want the derivative of tangent of 2x? Then you need to use the rule for differentiating tangent of something. The derivative of tangent of 2x is secant squared of 2x times the derivative of 2x with respect to x. So we have here cosine of tangent 2x, cosine of something, cosine of squiggle. The derivative of cosine of squiggle is minus sine of squiggle times the derivative of squiggle. So minus sine of tan 2x times the derivative of tan 2x, but the derivative of tan 2x with respect to x is secant squared 2x times the derivative of 2x, or 2 secant squared 2x. Okay, so let's look at these two problems again. We have here a product, cosine x times tan 2x. This has to be done by the product rule. First times the derivative of the second plus the second times the derivative of the first. This looks very similar, the next problem, but it's not a product. It's cosine of something. Cosine cannot stand alone. None of the Trig's functions can stand alone. They have to be followed by some function. Cosine of something. Okay, so since there's nothing else, this must be the f of x. This is y equals cosine f of x. The derivative is minus sine of f of x times the derivative of f of x. For our last example on this videotape, I'm going to do one involving implicit differentiation. If you have not come to implicit differentiation in your calculus courses yet, then just don't watch this particular example. But if you have studied implicit differentiation, you will be able to handle this. Y equals the tangent of xy, and I want to find dy dx. For those of you who have studied implicit differentiation already, then what we're dealing with here is a problem. We want to find dy dx, and our procedure is that we're going to take derivatives of both sides with respect to x. The derivative of the left side with respect to x equals the derivative with respect to x of the right side. Now the derivative of y with respect to x, that's just dy dx. The derivative of tangent of something with respect to x is going to be secant squared of that same something times the derivative of the something. Isn't that how we learned how to differentiate tangent of something? The derivative of tangent of something, secant squared of the same something, times the derivative of the something. But we have to differentiate the something is a product. So the derivative will be the first x times the derivative of y with respect to x, which is dy dx, plus the second y times the derivative of the first with respect to x, the derivative of x with respect to x, which is 1. Let's look. We have y equals tangent of xy. This does not define y explicitly as a function of x. All of the 9 other problems that we did today, y was equal to some function. On the right-hand side, we only had x. Here we have y on both sides. Y is not defined explicitly as a function of x. We're going to be using instead implicit differentiation. We take derivatives of both sides with respect to x. The derivative of y with respect to x is just dy dx. The derivative of tangent of something with respect to x is secant squared of that something times the derivative of the something with respect to x. But the something is a product. To differentiate that, it's going to be the first x times the derivative of y with respect to x plus the second y times the derivative of x with respect to x, which is 1. Now, we're not finished until we have dy dx alone on one side of the equation. And as you can see, we have dy dx here and over here. The calculus part is finished. The rest is just algebra. Okay? The best thing to do here would be to distribute the secant squared xy through the parentheses here. Remember, we have x dy dx plus y. We have like a times b plus c. It's going to be a times b plus a times c. So secant squared xy times x dy dx, which we could write as x secant squared of xy times dy dx plus secant squared xy times y, or y times secant squared of xy. Okay, once again, the derivative of y with respect to x was equal to the derivative of tangent of xy with respect to x, which was secant squared of xy times the derivative of xy, which is a product. We now distribute the secant squared xy through this parentheses, secant squared xy times x dy dx plus secant squared xy times y. Now, to solve for dy dx, let's get all the terms involving dy dx on one side. So I'm going to subtract this term from both sides and bring it to the left. So we'll get dy dx, which was already on the left. Now, after we subtract the x secant squared xy dy dx, it appears on the other side with a minus sign. So minus x secant squared xy dy dx equals y secant squared xy. Looking back over here, all I did was transpose this term to the other side. So I have dy dx minus this equals that. Dy dx minus x secant squared xy dy dx equals y secant squared xy. Now, since every term on the left side of the equation has a dy dx, let's factor out the dy dx. Dy dx times 1 minus x secant squared xy equals y secant squared xy. I factored out the dy dx on the left side, leaving us with dy dx times 1 minus x secant squared xy. If you multiply it out, you have dy dx minus dy dx times the x secant squared xy. And now finally, let's divide both sides of the equation by 1 minus x secant squared xy so that these go out, and we have just dy dx alone on the left equals y secant squared xy over 1 minus x secant squared xy. Okay, let's look this over one more time. We started with a function where y was not explicitly defined as a function of x. And we started with this equation, rather, where y was not explicitly defined as a function of x. We took derivatives of both sides with respect to x. dy dx was the derivative of tangent of xy with respect to x, which was secant squared of xy times xy's derivative, and that was a product. Here we ended the calculus. All the rest of the work was just algebra. We distributed the secant squared xy through the parentheses, the secant squared xy times x dy dx, and the secant squared xy times the y. To solve for dy dx, we wanted all the terms of dy dx alone on one side of the equation, so we transposed this term to the left side, giving us dy dx minus that term equals what's on the right. From the two terms on the left, we factored out the dy dx, and then we divided both sides by the 1 minus x secant squared xy, so it canceled out here, it appeared there, and then dy dx was left alone on the left, equal to y secant squared xy over 1 minus x secant squared xy, and that brings us to the end of this test.